Welcome to this movie on statistical mechanics. I am Jos Thijssen and I teach a course at master level on statistical mechanics at the Delft University of Technology. In this movie I want to derive and explain the virial theorem. And the virial theorem tells you how the pressure changes upon switching on interactions between systems in a gas. So if the particles in a gas do not interact, we have the ideal gas law, and we will get deviations from the gas law as soon as we switch on the interactions between the particles. And we will derive a formula which tells you how the pressure exactly will deviate. And the resulting equation, the virial theorem, is very important in doing numerical simulations of statistical mechanical systems. So we are dealing with the virial theorem for gaseous systems, and what we want to do is first we want to calculate the free energy, because from the free energy we can derive everything, including the pressure. We are dealing with a gaseous system, and the gas is composed of point particles, and these point particles are characterized by their momenta pi and their positions ri. And then we have the partition function z, which tells us what f is via this relation, and the partition function z is a sum over all the states of the system of the Boltzmann factor e to the power minus beta times the Hamiltonian, so the energy. And the sum over all the states of the system means an integral over all the momenta and all the positions. They cannot be distinguished more accurately than with an order of h. So in the phase space, this h to the power 3n is a kind of minimal cell in which we can distinguish different configurations, and there is also a factor of 1 over n factorial, and that takes into account the indistinguishability of the identical particles the gas is composed of. And so the task that we are set is to calculate this partition function. Now the evaluation of this partition function always proceeds along the same lines, starting by the integral over the momenta, and the reason for that is that the kinetic energy always has the same form. It's always a sum over pi squared over 2m, and therefore it is a product of Gaussian integrals, just like in the ideal gas. And so we can immediately write this partition function as follows. I've copied it here. We can write it as 1 over n factorial, and then we have lambda to the power 3n, and lambda is a length. In fact, it's called the thermal wavelength, and it has the following form. It's h over square root 2 pi m kBt, and h obviously is Planck's constant. So this is the form of my partition function. And the second part of the partition function, which is the integral over all the r's, that's usually more difficult because we don't know exactly what this form is. It can be anything, and it can contain highly nonlinear terms, and so there is no hope, of course, that we can find a general expression for this, but we can use it in order to find out something about the pressure. We can find this pressure from the free energy as P is minus dF dV, provided we keep the particle number and the temperature constant. And from F is minus, given by minus kBt ln Z, we can also find this to be P is d kBt ln Z dV at constant n and t, and therefore we find that P can be written as kBt That's just a constant when we take this derivative at constant temperature. And then 1 over z, because we have a logarithm, and then dz dv. And this shows how tremendously complicated our task is, because we have here an integral over all the particles, that each of which run around in a volume v. So v to the power n, that's the volume occupied by all the particles. We have a complicated interaction between the particles, it can be anything, and we need to take the derivative of this entire integral with respect to v. So it seems like an almost impossible task. Nevertheless, there is a way to make progress. So let's continue by just stating the result that we have. The pressure is given by kT divided by the partition function. I've left out the prefactors because we have 1 over z times dz dv, so the prefactors cancel. So the 1 over n factorial h to the power 3n or lambda to the power 3n that we had here, they are left out. They don't change the result. And then we have here the derivative with respect to v of e to the power minus beta u of r, and r, that is the positions of all the particles, and then we integrate over all those positions. That's symbolically indicated by this d3nr. So what we do now is we want to make this integrand somehow independent of volume. We want to extract the parts that depend on volume, and we do that by introducing a new coordinate, and this new coordinate is defined assuming that the volume V is just an L by L by L cube. And then we could define a coordinate Si for each particle, which is given as Ri divided by L. So each Ri alpha, so that is the Cartesian coordinate, the alpha is either x, y or z, that lies between 0 and L, and therefore the Si alpha lies between 0 and 1. So we can transform in this way this integral over all the r's into an integral over a hypercube in 3n dimensions. So we write P now as a kBt over Vn e minus beta u d3nr. We still have the derivative with respect to the volume, and we write this as e to the power minus beta u. Now, just as we lumped all these little r's into this 3n dimensional coordinate r, we can do the same with the Si, and so we can write the u as depending on L times S, where the S denotes all the little vectors. S1, that's the position of particle 1 rescaled to have coordinates only between 0 and 1, S2, etc. And then we have now a D3NS, but we should be careful because each of these coordinates is rescaled. We had R is L times S, so we should add here, because we have 3n coordinates, a factor L to the power 3n, and we know obviously, because V is L to the third, that we can write this as V in the power n. And so we see that part of the derivative with respect to V is now really explicit, because we have a term V to the power n here. Now we see that this expression here, of which we have to take the derivative with respect to v, has two dependencies on v. One is this one, and that seems rather straightforward. It's just a v to the power n. The other one is through this L. So remember that v is obviously L to the third. So if there is an L dependence, it means that it's also a v dependence. So this is a kind of complicated derivative. This one, however, is straightforward, and so we continue by first doing the trivial derivative, and we can write that as v to the power vn minus 1. But I'm going to write that as v in the power n divided by v, which is obviously the same, and then we have e to the power minus beta u of ls d3n s. Now we take a look at the second term, which gives us the derivative of this exponent with respect to v. And I've worked that out as follows. We first get the exponent, and then we get a minus beta, and then the derivative of the exponent of the u in the exponent with respect to v, and I've used the chain rule to first take the derivative with respect to ls, and then the derivative of ls with respect to v. And so you should always keep in mind that s is a long vector which has 3n components, because it's n three-dimensional vectors, and so this gradient contains in fact 3n components, and this vector here also contains 3n components, so that we have a dot product. And so now we can first have a look at the first term, which turns out to have a very simple form. In fact, the combination v to the power n times the integration over the scale variables, we now return back to the original notation. That can be written as d3nr, and we see that this integral is exactly the same as this integral, so this integral cancels against this one, and so we can start the next line by writing p is kbt, and then we have an n over v, and since the integrals cancel, we have here simply a 1. And so the next term we should deal with is this more complicated term. But before we do that, we emphasize that in this equation, suppose that there would be no correction, you recognize the ideal gas law, P is kTn over V. And so we see that indeed the presence of the U gives us a correction with respect to the ideal gas law, which is written here. Okay, then we tackle the second term. First of all, there is a factor of 1 over kt, so that should be incorporated here together with the minus sign. So in addition, we have added to the kt, which was already there, an n over v, so that will now be a v over n in order to compensate for that. And then we need to introduce the e to the power minus beta u ls, which was obviously there, and realizing that the s is a long vector, we can write the derivative as a sum of du dri, and then we take the dot product with d and the ls. That's in fact the vector, the long vector capital R, so that has components ri, dv, and then we have v in the power n. Well, in fact, the v in the power n d3ns can be written as d3n r, and then finally we have to take into account this factor here, which was here in the denominator and which we have left out there, so it should be restored e to the power minus beta u of r d3n r. Now the main difficulty which remains is to work out the derivative of dri with respect to dv, and we do that as follows. So we now work out this derivative, the dri dv, and we realize that the ri can be written as L times Si. The Si is independent of v because that's a coordinate within the unit cube, and the L, however, depends on v because L is v to the power 1/3. And then if we take the derivative with respect to v, we immediately recognize this as Si over v to the power 2/3. We restore the L in front of the Si in order to get Ri back again, and we get 1/3 Ri divided by V. And so we can restore that into this expression in order to get the virial theorem in its full form, and that's nkt over V. And then we have first the ideal gas term. And then we have, well, this factor of V cancels against this factor of V. We have an extra factor of 3. So we have 1/3 nkt and then we have in fact this complicated fraction of the two integrals, but we recognize this is a Boltzmann factor, integrated, but here there is an extra term, so it is just an expectation value of the term sum over I du dri, and then the dri dv, that was my ri. Well, the v had already cancelled, so this is simply times ri. And so that's the final result. And this term of which we take the expectation value is generally known as being the virial. And it turns out that for attractive forces this gives a reduction of the pressure, for repulsive forces this gives an increase of the pressure, as you would expect. Now we would like to consider in particular this virial, the expectation value of the virial, and specify its form for the case that we have pair interaction. So in many cases we approximate the real potential acting between the particles as a sum of two particle interactions, like here the v, which depends only on the relative distance between particle I and particle j. And in order to avoid overcounting, we take I smaller than j. Now let's work out the virial for this particular case. Then we see that in the case that I is indeed smaller than j, we get a vri minus rj times ri. And then if the I is larger than j, we get in fact a similar term, but then the j is in front. And so we see that with respect to this term we get an extra minus sign, because here we have ri with a plus sign, and here we have ri occurring with a minus sign, and we take the derivative in both cases with respect to ri, so they have a relative minus sign. And so some inspection then leads to the conclusion that I can write this in the following form. We only sum over only each pair once, and if ri is say the smaller than the j, we get this one. J in this case is larger than I, and it occurs with a minus sign. And because all the particles are identical, we expect that this term is in fact the same for each term. So in fact we get the number of distinct particle pairs, which is n times n minus 1 over 2. And then we could just single out one pair. For example, dv r1 minus r2 dr1 dot product with r1 minus r2. And because it doesn't matter which pair we are looking at, we could also write this as the integral with a prefactor of n times n minus 1 as an integral of gr times dv dr, and this is in particular in the case where v depends only on the amplitude of the distance, so v is v ri minus rj absolute. Then we can write this, and that's very often the case, then we can write this in the following form: dv dr, and then we have d3r. And what is g? Well, g is the probability density of finding a pair at a separation of r. So in formula we can write g as follows: gr is in fact an integral weighted with the Boltzmann factor of all the positions of all the particles, but now we restrict ourselves to those configurations in which particle number 1 and particle number 2 have a distance that is exactly equal to the r, the argument of g. And so it makes sense to interpret this. It is in fact just a probability density for finding a pair at a separation r. And so if we use that to g in this equation and then use the fact that for particles that have an interaction that only depends on their distance and not on their orientation, we can in fact the g will only depend on the distance, so we can do the angular integration as usual, and we would get minus 1 times n. Then there is here a 2 pi r squared gr dv dr dr, where I've used the fact that in 3 dimensions the volume element can be written as 4 pi r squared dr, and then the 4 pi together with this factor of 2 gives me a 2 pi. And so this is a very useful formula which is often used in numerical simulations. So what happens in numerical simulations is you often want to know the pressure, and the obvious way to calculate the pressure is to just put particles in a box, let them float around, and then once a particle hits the wall its velocity is reversed, and then you look at the delta p, the momentum change at collision. You add up all these delta p's within a certain interval, so you get all kinds of momentum changes, and you divide that by the time you have waited, and that by definition is a force, and the force is the same as the surface area times the pressure. And so this is the way you can find the pressure. You just look at how the momentum changes at a wall. However, this formula has 2 drawbacks. First of all, in simulations we often do not want to have walls. What we do is we use periodic boundary conditions so that a particle that flows out of the volume enters on the other side. And the second problem is that even if you would then just calculate the momentum transfer, just pretending that this particle would reverse its velocity perpendicular to the wall, that would still give you a pressure. But if you have a large system, there are not that many particles close to a wall, so you have only a small fraction of the particles participating in calculating this average for the pressure. And therefore, if you calculate in this system, the correlation function in your simulation, if you measure the correlation function in your simulation, you can use that in order to find this expression for the pressure. And you could even do this directly. So within the simulation, you can just calculate the expectation value of the virial, and the big advantage of this approach is that each particle participates in the calculation of the virial. And it's not only the particles that are close to the wall that contribute to the evaluation of the pressure. And so that's one of the main uses of the virial theorem, that it gives you an opportunity in numerical simulations to calculate the pressure.